Let me just hide the video and also this one. Okay, good. So what is on the menu in this course for this next week? So today, my ambition is to somehow finish the standard logic part of the course. So we will continue this example that we started last time, and so in the first half of the class, so we do some recap on what we did last time, and maybe have a closer look into conjunction normal form. So this is something we didn't do last time, and then so I want to give you a kind of brief introduction to fuzzy logic. I mean, so this module is being under development, so this is new for this year in this course, and in the future I plan to introduce a lab on that. But this year we don't have lab, so it will be more of an introductory point. But again, the idea is to make you somehow curious about other type of classical logic, and maybe, I mean, you can get more insights through self-studies, and I will give you some good references to for the introductory video as well. But all in all, I mean, still, as I started in the introductory class, the idea is to the main idea I want to plant in you is the diversity, the richness of reasoning. So how much and the complexity of what we call by reasoning in us intelligent being, and the complexity of creating this artificial intelligence in general, or artificial general intelligence, if you wish. So let's get started. Our example again. So we have this agent discovering this little world. So by the way, have you started? I saw your posts on Discord. So you have started with Lab 1, right? So Phil should be kind of complementary, but to this one. So this is our small world that the agent discovers, and on the example of this world, so we introduce the major concepts about reasoning. So we have a knowledge base containing the rules, and here we still talk about propositional logic, and in propositional logic we have all our variables in binary form, which takes either true or false assignment if they are known, or being discovered with time. And then we have a concept of entailment. So let's see how it's going. So I have a couple of slides on this recapitulation, because I think this concept is very important to have a good intuition about. But the entailment means that all the rules that we produce, they should be supported by the knowledge base. And I want to link to our kind of online discussion last time, and again, warn you if you didn't work with this before, or maybe again on part of recapitulation. When we approach solving such problems, I mean, reasoning or logical inference, we can do quite many mental steps And in a way, these steps, they may result in a kind of shortcuts to conclusions that we think is kind of obvious and to hold. In logical agents or in reasoning, in computer-based reasoning, so everything should be supported by particular rules. So any new rule should be supported by the existing rules. And that's why we do all these troubles of inferring. So basically combining the existing rules, so starting with some small set of rules and discovering new facts. So I will not spell this example as we did last time, but rather I want to continue on this example and talk about resolution. So how the inference is working as a program. So the key to algorithmic reasoning is to modify basically the rules into a specific form to which we can apply a resolution rule. And a resolution rule, so it is spelled out here. So it takes two clauses, so two set of rules, and this clauses is disjunction of literals. And we do two things with this. First of all, we remove the complementary literals. So basically, if we have a variable and its negation, so it cancels each other, as simple as that. And we also factorize, so we remove multiple inclusions of the certain rules, of the certain literal. And this may appear as a result of resolution, so as it is demonstrated here. So if we have a term A or B, and at some other point we have a clause A or not B, then so B is cancelled, and then we obtain so multiple copies of the same literal, so which is further reduced to A. So this is factoring. So elimination of complementary literals and factoring. And the important thing here is that the rule applies to disjunctions of literals, and that's why. So we need to convert rules which otherwise could be written in, for example, in this form. So rule 6. Or, well, basically rule 2 here. So if and only if kind of rule into the form which allows resolution. And so one of these forms, normal forms that we need is a conjunctive normal form. So and on the level of definition, so we represent a logical sentence as a conjunction of clauses. So first exercise for us, maybe, I don't know, let's see if we have like 5 minutes maybe, and try to convert this clause into conjunctive normal form. So please, I mean, so you see it kind of naturally grouped in pairs. Some of you sit alone. That's fine as well. So 5 minutes, or maybe some more. So conjunct this can transform this simple sentence into CNF. And maybe let me see. I can also. Oops. I will move this thing for your help. Oh. So this one is needed as well. So let's do an exercise. And once again, so sorry for distracting you. So I think this thing worth an explanation somehow. Within the scope of this course, I really kind of want to remain on the level of rather small examples. So just to give you a feeling, or to have some recap from your previous courses, to give you a feeling about the main concepts. So even on the test, you probably shouldn't expect way more difficult examples, which require more complex calculation. Yes, classical and standard logics are same words, same terms. And one slide up. It'll take 3 more minutes. We take one more minute and then we go through. So, shall we go through this example? So, help me out. A sentence is very simple. So, you smell, you have a bad smell, if and only if in either of the neighboring cells you have poison. So now we want to convert it into CNF. So how do we approach it?
First, we can use by conditional.
Yeah. So eliminate by conditional intent implication, not intent, it's implication. Yeah, that's different thing. Right. What would be B1? So implies P1, 2, or P2, 1. So that is the first thing, and basically P1, 2, or P2, 1 implies B1, 1. Next, we take care of these ones. Yeah. Like this. Yeah. Yeah. I mean, yeah, of course.
Implication elimination.
Implication elimination, which is you negate the left-hand side. P1, 1, and or sorry, P1, 2, or P2, 1, or so you negate this stuff over here. Yeah. B1, 1. Now, this thing, the negation in CNF can appear only with literals, with the variables. So this needs to be corrected or simplified, and we have this the De Morgan rules. Yes. Better. Equivalent. Or not better. And similar thing. So this thing over here, so that's that would be applied to this guy over here. And so then we apply the whenever possible disjunction over conjunction. So the final form we have is not B11 or P12 or P21 and not P12 or B11 and not P21 or B11. So this is the CNF of this thing. And this will be obviously posted as PDF after the class. And so just maybe looking a little bit ahead. So soon we will be again recapitulating on the concept of entailment. Yes.
I have a question.
Yes, there was
Yes.
an error in the solution you gave.
Like, if you do like De Morgan on
Mhm.
the thing in the parentheses,
Mm-hmm.
we got like a different result where you would have like the first part and negation of P12.
Let me maybe do this one.
Yeah, so. Okay.
Did I miss anything?
Could we use like De Morgan
Mm-hmm.
and then we have like can I go on the board and just
Yeah, sure. Yeah, go on. Yeah, you can even if you want, you can use the screen to write.
so
Yeah.
we have the first part like with three values, you know.
Yeah.
And P2
What?
or so here is like De Morgan, right? Negation and
You need to spell out first the whole parenthesis with De Morgan.
this,
So this thing.
And how will that be? It will be minus. Yeah, we'll turn this one and not
Mhm,
you want to, right?
mhm. Yes.
And the
I'm sorry.
okay. Yeah, I thought we got like,
Yeah.
but we have to use distribution here. There's
Yes.
no other way.
Yes.
Okay. Okay, I think.
So
Yeah,
you
because
need to use the distribution, yeah,
Yeah,
to
yeah.
open the parentheses.
yeah, I think we used
Hmm.
the Morgan wrong. I think we just did it on one.
Yeah.
Yeah, okay.
Yeah.
Okay.
Yeah, sure. But once again, that's good. So keep on kind of having this intuitive understanding. We won't go into very complicated examples. It's frankly, I mean, complex even for me as well. So to simplify, complex equations, very simple to do. Very easy to do mistakes, obviously. But again, so what we do here is to, yes.
And just with the resolution rule, after we have like simplified then we can apply the resolution.
Yes. Yes, and that's what I wanted to conclude with. So when we have converted it to this form, so conjunction of disjunctions, so we apply. So we ready to run the resolution algorithm, basically. So we where we take all pairs, all conjunctive terms, and apply the resolution on them pairwise. And so the whole the first step we do is is that we apply the rule, the proof by contradiction. So if we want to see if our knowledge base supports certain sentence, so we negate it and prove conjunction of these terms. So again, maybe I will not spell out this textual thing. So here is an example. Again, this is example. I think you can find it in the book as well. So apply to this rule. So yeah, let me see. Will there be in midterms exam exercises on? Yeah, short answer is yes. There will be. And again, a bit longer answer would be still, as I mentioned, on rather simple levels, so no complex simplifications. So the idea is really to renew the basic rules and fundamental manipulations of logical sentences. So, but here is the resolution algorithm. So you have the conjunctive terms and the fact that you want to prove that there is no poison in this case. In 1-2, and you do it by pairwise resolution, so of disjunctive terms. So eliminating negations and factorizing, so removing the multiple literals, and at the end what you want to have, so if proof by contradiction succeeds, then you need to have you will end up with an empty statement there, where all terms will cancel out. Yes. Let me see. So we have, soon I will let you go on a break, but before I conclude this standard logic part, or propositional logic, standard logic is a broader term, so it includes many logic flavors in itself. But so you mentioned this term entailment, which I think is also important to have intuitive understanding. So these simple sentences over here. Again, so we just operate with two variables, and this is made up example again, just to use different literals. So if you have money, you go to a party, or you go to a party if and only if you have money. So these three questions, again, so 5 minutes. Tell me, so which of these sentences, which of these cases is true, meaning that the left-hand side entails the right-hand side. Or left-hand side supports the right-hand side. And to remind you, so the first bullet point is about the definition of entailment. Yes.
So like the minus.
Where is minus? No. It's a sub bullet. It's no, it's not a minus. So there is no minus in logic. And not, it's not. No, it's not negation. I need to maybe. Let me see if I. Can you maybe tell me just before you do calculations, and here you actually need to do calculations, so it's hard to, well, you can do it all in your heads, but it's, I mean, to be sure about correctness of answer, is best to do some calculations. What would be your approach? What would, yes?
The case where in the first one there's only one case where E and N is true. That's when
Yeah, just let me rephrase what you say. But I mean, if we talk about approach, that is correct approach. First, to find out in which cases the left-hand side is true. So, and then obviously the next step is to find out in which cases the right-hand side is true. And then you compare these two cases. And entailment only is true if as it's written here. Let me just read it, not to confuse you. If all true cases of the left-hand side are also true in the right-hand side. So let me just P M. So again, P M and M P and not P or M and not M, not M. Oh, or P. So P M P M P M P. What was it? The first one, and M. So let us enumerate the models. Basically we construct truth table, and again, so do this when you reason about sometimes you can do mental shortcuts. So some cases, some examples could be like evident. So that's, I mean, only I mean that's I mean the right hand side fully contains the left hand side, so you can just tell. I mean, but in all cases, the best approach is to spell it out. And again, in this very simple case, you just enumerate all the models. So 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. So and that's easy, right? 0, 0, 0, 1. So what about the truth table for the right hand side? 0, 0, 1, 0, 1. False. Yeah. Yes. 1. Okay. So you see they have different outcomes, obviously. Now back to the question. So P and M entails P M. Is it true or false? True. So all models in which left-hand side is true is also true in the right-hand side. What about if we swap? Yeah, if we swap the sides, it becomes false. Why? Do you see why? Because you can find the cases. So if you swap to P M and entails P and M. So you can obviously find the, so you have one case in which left-hand side becomes true and not the new right-hand side is true. So, and that's why it cannot entail this statement. So that's again important concept. And entailment is really the fundamental concept of reasoning. So entailment meaning that your set of rules support certain outcomes. So okay. Let me see. Let's go for a break. So flash our brains a little bit, and after that we will talk about something different.
How long will be the break?
How long will be the break? 5 minutes until 11:05. And I forgot to copy this. Yes. So the as an answer to you in chat, yes. Only the first sentence was true.
Yeah, thank you.
All right, shall we resume? Yes, we continue with standard logics. Or basically now we look into another variant of classical logics. And so far we were talking about propositional logic. So where we have variables that describe facts or percepts about world situations. And so we could write statements about these facts and percepts using logical formulas. So we have this or not implies operations. So what was the main limiting factor for the propositional logic? So what was so special about these variables so far? They were of binary type, so they either hold or not hold. I mean, maybe they are known. So in many useful cases, we deal with more complex situations. So we deal with values and we deal with uncertainties. And again, so I mean, it's part of your home assignments to read about different ways to, yes.
There's something called natural kinds.
Say again?
Natural kinds. In the book, it's like, for example, a tomato is usually like red and round.
Yeah.
Yeah. I don't know if that's, we heard of that concept, or we call it something different?
Which one? Say again. Can you say again?
Animal theory, vision theory. They describe it as a natural kind logic. I don't know if you've heard of it.
Natural logic, or
I think it was more the knowledge representation of
Yeah.
the
Natural kind.
triangle has the
Yeah, yeah.
Kind categories.
Which category? Sorry, Sure. Yeah, but what
Like, is that what you usually call it, or do you, when it's not exact, you know, it's not exact, yes, like,
yeah, on a level of definition, if we usually call it, yeah, yeah, they are obviously natural kind categories, which are much richer in their structure and values compared to binary binary variables. Yeah, as a global class, yes, they are natural kind of concepts. Here, and again, so there are different ways for describing or in baking these categories into logics and reasoning. What I want to talk about now is is a special way of dealing with uncertainties in these natural kind of variables, because if you read this, actually this information is also spread in across different chapters. So you can, so in some cases you can describe these categories using concrete values. So if you kind of know for sure, for example, the operating ranges of, or the range of possible values for certain facts or precepts. Here, what I want to introduce is a special kind of, and then you use obviously like intervals, exact values, and other types of higher order of logic to deal with these cases. So here I want to talk about some less quantifiable categories. So categories where it is at least hard to define a specific value for. Why this situation is happening? Well, because of different reasons. But again, so first thing first. So we consider a logic of this kind, so which is more natural to us, I mean, in everyday life, because we operate in, okay, so I will use this in rather non-exact terms. So if dishes are dirty, use hotter water. If there are many dishes, use more water to wash it. So how to, and the question is how to build a logic and encode these terms into specific values. And of course, so if I will jump over to this case, so in or to this slide, in some and many cases, you can find quite accurate values for the categories, for this natural categories. So you can measure pressure. So you have your units of measurements. You can measure temperature. You can measure rotation, and yet we have many cases where these values, they are I mean, they cannot be derived in an exact form. So how come? So if we, so here is the list of possible reasons. One possible reason is connected to the errors of measurements themselves in devices, in electronic devices. So you know, if you have many sensors of the same phenomenon, the temperature, still, I mean, they will all report different values depending on their calibration, depending on the quality of circuitry, electronic circuits that are used. So they will report these measurements in a given in a certain range. And of course, in many practical cases, well, talking about this sensors, I mean, one way of doing this is to calibrate the system, so you can introduce say mean value for the measurement. But there are cases where this mean value is not enough. So you really want to be more expressive and consider the border cases. So where you are not interested in just mean values, but rather values in between, which may correspond to different categories or different concepts, basically. I personally found I watched different tutorials. So some of them are more mathematical, so some less. This link over here, I found it very useful. So it uses MATLAB as I mean, it's not really kind of hand waving stuff, rather applied tutorial, but presented in a very good, concise way. So, for example, in this tutorial, he uses this example with credit risk assessment, where exactly the situation of mean values for the risk is not good enough. So, I mean, it implies, for example, two drastic decisions, for example, whether to give a loan or not to give to a certain person, while there could be some border cases where while say credit history looks okay, maybe still it implies a higher risk. So there are many life situations where you should deal, or we deal with uncertainties. So first question to you, just again to facilitate our discussion. A concept of old. So I think we are pretty much homogeneous with the age here in the group. So how you define, how can you quantify this concept of old in years? I mean, what is old for you? Yes.
And when you stop working,
Still, it's a kind of so what which age? 65. So let me just I never did this exercise, so let's see. Yeah, let's see if if we succeed. So let me just write down all suggestions. So 65, more ideas. So I want to hear some numbers from each and every one of you. So let's start with you. So say you said already 65. What's your old? 80. Okay, 80. Yours? 70. 70. Anybody else who thinks it's okay? So let's continue here.
Well, my first thought was late 30s.
Okay. Late 30s, like 39. So you're old, experienced, not old. Yes. What about you?
70, but I don't know if old is right. I would say older. Like
No, old. No, I mean, here it's not comparative. It's old. So when the person is old, he needs to retire. Yes, whatever. Yes. 75. Okay, I like this. 75 more. Okay, 75. That's fine. 60. 60. Yeah. 73. Okay. 73. 55. And again, so I will now do a very 70. Okay, let it be 70. And you guys? 60. 70, 60. Yes, okay. So we 70 70, 60. 60. So let me see. Again, so I didn't prepare any MATLAB script or whatever, so should have tried Excel at least. Yes, let me see. Yeah, so what kind of what is that? Remind me later. So let's see. We have this age variable, and then we have, say, What is the mean? Like 70 here, probably. But let's see. So we have between certainly between 40. No, we're talking about concept old so far, so no young. So so we have 40. Here we have maybe 80. 80. Here we have what is it? 60, right? 50, 70. So what do we have here? How what is the winner here? 70 we have, right? 70, 75. So 70 we have like one, 2. Okay, so we have also 75 here. What is it? 1, 2, 3, 4. So say 4, 70. So like this. So we have 4, 75, 1, 2, 75, 2. 60. 60 we have quite some, right? 2. 60. And then we have some 65. Yeah, some small numbers. And we have 180. And one even 39 somewhere here. Yeah, you got the point, right? So we do measurements. So we ask as experts about different concepts, and so we do simple statistics. But what we also do, so we probably normalize it so that we have bounded variable between 0 and 1, or 0 and 100%, 0 and 1. And so we have, well, then we have a different case. So we have this, so around 70, then we have 80, and then we have 60 somewhere here. And I have it and a tail somewhere. So so these are still measurements. Then we can fit a function. So just that describes collectively all these measurements. Functions can be, as you can imagine, so they can be different. So what are the possibilities here? For example, something like this, maybe. Yes. Or maybe, I don't know, if you want, it can be like this even. So just to keep it simple. Simplicity is one of simplicity of the function that describes this expert poll is one of the decisive points later on for the implementation. You can use, for example, a smoother curve. So like say Gaussian. But the whole point is that you somehow describe all these different opinions of given by experts using certain function. So remember this. And so to us, so this function would indicate old. So in the same fashion, you can describe function young or middle age. So and then obviously, so you will have you will have different functions spanning different intervals, right? So one for say middle age or young, and collectively, so they I mean, this set of functions would define our category of age, right? Yes, and again, looking, well, not looking a little bit ahead now, I will just fast forward the slides. But this function, so each and every function is called a membership function for a concept. So you or for a variable. And here it's important to differentiate two types of variables. Exact variables, so for which we can really quantify its value, or linguistic variables. So we call them linguistic variables, where which assume certain range of valid values, and takes into account opinions of experts on this age. So it's, you see, it's not homogeneous here. And now we want to build a reasoning system based on this kind of variables, and it is useful in many scenarios. So it's not for by chance I give an example with some complex electric machine, well, more or less complex electric machinery. So it can be a motor controlling elevation of a lift. So it can be again a motor controlling a train. It can be a software piece that decides that certain set of pixels belongs to an edge of a face. So and so basically, all in all, so these variables it give you a kind of score, or these functions, they give you a score to a linguistic variable, and then you can build the entire logic system based on these values. So let me see. So we are about to implement our logic in terms of this kind of if and, or if logical predicate, then type of rules, and this kind of definition for the categories or and concepts. So a membership function, so on the level of definition, again, so this is my digested definition. So it's a function that describes subjective judgment about linguistic variable. So it can be anything from, let's say, credit risk to, say, ripeness of apple. So I use this example later on, to deliciousness of a food in a restaurant. So something with really with a great deal of subjectivism in its definition of the values. And so this function map the scoring of some exact value. So like in our case, it was age. So age is an exact value. So 60 years old is an exact value, into certain scoring of this linguistic variable. in other words, introducing the fuzzy range. And once again, so here can be different use cases or applications. So in the case of a restaurant and grading the quality of food, or say if you judge on the service in a supermarket, so you grade it within certain category. But the same applies even for temperatures. So in many tutorials or in some more mathematical tutorials, so they consider, for example, controlling air conditioning system, so based on this kind of rule. So if the room is if the temperature is higher than usual, then reduce then cool the air. If it's lower than usual, then heat the air. But all in all, so it assumes this fuzzification step of mapping from crisp values to fuzzy concepts. And again, so for next discussion, so I decided to use this kind of example where you have apples with different ripeness levels. So ranging from being unripe to kind of perfectly ripe to overripe, and what you can do with these apples, sorry. So for example, unripe, so if you again, so all the membership functions you construct based on talking to experts. And then you find the most appropriate approximation of this data. So normally it involves, in many cases, so it involves certain reference or kind of mean values and certain distribution around it. So that would be our concept of ripe and overripe again. So after certain values, so it's just overripe for sure. So all agrees that, for example, in our age case, so pretty much all would agree that after 85, so the person is old, whatever. So whoever you ask. So. But again, so the shape can be different. So for example, for ripeness, it can be trapezoidal shape. Sometimes it can be a triangular shape. In cases, in some cases, it can be Gaussian shape. So it can be skewed to the triangle to a certain side, etc., etc. Here is the list of possibilities. So if you go to MATLAB toolbox for fuzzy logic, and different well, you don't I don't see it myself, so don't be stressed that you don't see it. So go to this link offline and check it out, different possibilities. But the idea is that it's up to the developer of the system to choose one of the shapes of the function that performs best for a given application and describes best in a best way opinions of experts. And then so we started by defining the membership function. So in the same way, you can define a fuzzy set, so describing a certain concept. And this is basically a collection of function and certain, say, centroids for the concept. So this is pretty much, I mean, you can find, again, pretty much standard ways of describing range of values. For example, whether it's voltage supplied to a motor or room temperature. So you can always define, for example, range in the lower negative end, so middle negative, then centrals, then medium positive, some large positive. So, and the point is that so these concepts are intersecting. So that this is the whole thing. So these intersection areas, so they over here. So it is where the experts disagree. So some people agree on one thing, and other people agree on the other thing, or sensors disagree. So in values. But that is the way how we actually come to the formalize in the reasoning in this case. So let me. Yeah, I will come back to that slide later on. So you have your knowledge base. So this is if then rules, and if predicate or predicate then action rules. Then you have certain measurements, the transformation into this fuzzy domain, so in fuzzy variables, based on the previously defined categories. You apply special special algorithmic way of processing the rules from the knowledge base, and by the result of this rule, so you end up with again with a distribution which rules are most applicable to say a given precise value in for a given concept. And but then in many cases so you need to kind of, so your system should give unique answer, so it's kind of directly interpretable. So it needs to kind of summarize all the rules that are applicable to this value and give a recommendation. So that this is the overall algorithm. So let us quickly go through this simple example. So we have this 3 rules, and the system is about actually suggesting or giving a recommendation in terms of profit. Again, so I mean, you can kill this idea. I thought it's, I mean, it was my own reflection on some other examples, but nevertheless, so on the one hand, you have this fuzzy concepts of ripeness of, well, in this case, apples, and at the very end is the profit that you can get based on what you can do with these apples if you harvest them at particular moments in time. So what you can do with them, you can either so if they are overripe, so you can do cider. So if you're perfectly ripe, so you can do juice, or, well, in this case, juice. Or if they're green still, you can use chutney out of them. So how do you do that? So you started off with characterizing these concepts, these linguistic variables, overripe, ripe, unripe. But now your system gets an exact input. So again, the ripeness score. So that's subjective, but it's at least, so this is a crisp variable. So the variable in specific range. So from 0 to 100, say. And so you want now to map given score into possible fuzzy concepts. So say you pick an apple or a set of apples, and you decide that so its ripeness score is well, this one, I don't know, maybe 70. So what do you do then? So you have this collection of you have a fuzzy set describing this variable stored in so by the side of your knowledge base, and then you basically do this mapping of your score into the concept. So you basically say that this specific score corresponds to say 20% of being ripe. So 20% of people regarded it as being ripe, and 80% of being overripe. Okay, overripe. So, and that is what is called a fuzzy variable. So from a given single input, so you consult your you consult your fuzzy set. So you collect set of functions, apply these functions, and so in this case you have three concepts. So it can be many, like in the case of this values in given interval. And then you basically do the measurements for each concept. So okay, so here, so it's 0% of being unripe. So it's 20% of being ripe and 80% of being overripe. And then, so what do you do? So now you have this fuzzy variable describing a specific input, and then you can apply the rules in the database. So compare it to the propositional logic that we considered before. So you apply it in a sequential manner. So you kind of so you take everything what was known previously, so do some transformations and derive new facts. So here you have the rules, all the rules, all the facts exist in your knowledge base, and for a given fuzzy variable, you need to collect all the rules containing this linguistic variable, so all of them at once, and make a scoring of them. So to which extent they are applicable, or the results contribute to the final decision. So, and this is a simple example. So if we have again, so to produce either juice or chutney, and you apply this fuzzy variable to introduce the importance of the rule for the final decision. So basically, 80% of the rule to make a cider and 20% of a rule to make a juice in this case. And this is the output of your fuzzy reasoner. So which of the rules from your knowledge base are applicable to this particular input? But again, so this is just an intermediate step. So it doesn't tell you, so it requires further analysis. So what does it mean? I mean, that these rules are applicable to this degree. And so coming back to this illustration over here, so you need to differify. So you basically need to interpret this outcome in a form of a value, and that's how you can do it. So there are different ways again here. So if you go basically there can be an entire module developed just for fuzzy logic, because there are different ways on how to well, construct the functions, so the membership functions, but also how to interpret the results. So the defuzzification involves yet another fuzzy set, but now for the output, for the output concept. And again, in this example, so I chose a dependency of say of the profit. So if you are selling all these products that you do of different types, cider, juice, or chutney, so you can get smaller or higher profit, so to say. So, and again, this set is constructed, this fuzzy set is constructed by after statistical analysis of historical. Yes.
So determine what is most valuable to make. And you just look at that triplet of value and see which value is like the highest.
There are different concepts. So one of I was just about to tell. So it's called Prodmax or Prodmax rule. So what you do, so this is the fuzzy set describing the profit. So that's what you want to determine. So you want to determine the value here based on the outcome of the reasoning about specific products that you get from the reasoner. And what you do then, so you start to fill in the shapes, so the areas for a given product to the degree to which this rule is applicable. So, for example, if we have, if our fuzzy output tells that, okay, so it's 0% of chutney, so you don't account for this, for the influence of this concept in the final decision at all. So you take the value of 20% of the area of the juice concept, and 80% of the area of the cider. So you need to take the area, so you, basically all the possibilities, so on both ends, because you don't know that. And what you do, so you merge them together. So this is your the decision surface. So it incorporates the profit that you get out of juice to this degree and profit that you get out of cider to this degree. And then what you do, so you really find a center of mass, so to say, in this. So you take in well, it's an integral. So you compute the area of this shape and find its centroid, and it becomes, so finding the x coordinate of the centroid would give you the outcome that you need. So it's not that you kind of interpret it one by one, but you interpret the entire outcome of your reasoner, so per concept. And there are other different ways for constructing this this area and computing the crisp outcomes. So you can find it in either MATLAB toolbox description, or I think in one of the YouTube tutorials also they talk about this. But now, so if you just roll back and I don't have time for that. Just the last word to say. So this can input and output can be connected to a specific process that you want to steer with this system. And in this case, you come up with a fuzzy control system, which is really used for controlling complex devices. But again, if you want to know more, so please go ahead. So this is the task for your self-studies. I find it very cool. But all right, that's it for today. Next time we start with ontologies and semantic web. So let me see, stop sharing. I want to stop recording.